In this video, we're going to look at how to solve an exponential equation. So an exponential equation is an equation that has the variable up in the exponent. And the whole idea of solving this kind of equation is to get a common base. And once your bases are the exact same, then you can set your exponents equal to each other. So just a quick example on the side. If I had 5 to the power of 4 equals 5 to the power of x, I have a common base because both of the bases are 5. And because I know I need to solve for x so that left side equals right side, the minute the bases are the same, the only way that the left side will equal the right side is if the exponents are equal to the same thing as well. So in this simple example, x would equal 4. That way, if I did 5 to the power of 4 on the right side, it would equal the left side. Now, the whole idea of this is that sometimes you're going to have to change the bases so that they are the same. So knowing your exponent table is very important here. So let's try the first one. 3 to the power of x equals 81. 3 to the power of x, I can't do anything with it, but I know that I can rewrite 81 as 3 to the power of something, and 3 to the power of 4 is equivalent to 81. So I just did a little swap there. And now that the bases are the same, I'm just going to set the exponent on the left, which is x, equal to the exponent on the right, which is 4. And now you have isolated for x, so you are done. If we look at the next one, my bases are already the same in that they're both 6, but my exponents are a little more complicated. So I'm going to set my exponents equal to each other. So 2m plus 12 equals 5m minus 9. Now it is a grade 9 skill of isolating for your variable. So I'm going to bring my m's to one side and the constants on the other, so that I have 2m minus 5m equals negative 9 minus 12. And when I clean that up, I get negative 3m equals negative 21, and then divide both sides by that negative 3. And when I do that, m is equal to 7. And you can always do a left side, right side check here by subbing in 7 into each variable and then checking to make sure that when you do 6 to the power of whatever, it's the same thing as on the right side. Okay, let's go to the next one. So if you go to the next one, we see that the exponents are a bit more complicated with the 6 minus x and x minus 3, but this time our bases aren't the same. But I do know that I can rewrite 49 as 7 squared. So that's the first modification we are going to make. And I'm going to put that 7 squared in a bracket and then x minus 3 outside. Now we have to think of our exponent rules. And it says that when you have an exponent to the power of another exponent, you should multiply your exponents. So here I have to pretty much distribute that 2 into the outsides exponents, so that I have 7 to the power of 6 minus x equals 7 to the power of 2 times x, and then 2 times negative 3 is negative 6. Now my bases are the same, so I can set the 6 minus x exponent on the left equal to 2x minus 6 from the right. And then again, we're back to grade 9. So I'm just going to bring the x's to the right this time and the constants to the left just to make everything positive. So 6 plus 6 equals 2x plus x. So I have 12 equals 3x. And when we divide each side by 3, we get 4 for our x value. All right, if we look at our next example where we have negative 2 all to the power of x equals negative 128, our base is negative 2 on the left. So I have to turn negative 128 into a base of negative 2, which is already a clue to me that the exponent should probably be odd. So negative 2 all to the x is going to equal negative 2 to the power of 7, because negative 2 all to the power of 7 is negative 128. Now that my negative bases are the same, x equals 7. and that's it. Now, if you look at the next one, you will see that there's this random constant on the left side. You cannot get a common base and set your exponents equal to each other unless you have a term equals a term. Like we had in all the other examples, there is nothing else on the outside being added or subtracted or multiplied. So my first step here before I'm back to basics is to bring this negative 10 to the right to join the 26. So that I have 6m plus 12 equals 26 plus 10, which is 36. And this is actually perfect because 26, I couldn't do anything with it, but 36 is the same as 6 squared. So I'm going to go ahead and do that modification. Now I can set my exponents equal to each other. M plus 12 equals 2. Let's bring that 12 over and it will become negative 12. So 2 minus 12, negative 10. And there we are. All right, let's try some more. So in all the other examples, we only had to modify one of our bases to match the other. But if you look at our next example, we have 32 as a base and 8 as a base. I cannot turn 32 into 8 to the power of something because 8 squared is 64. I've already gone too far. So sometimes you have to change both of your bases. So 32, I can write it as 2 to the power of 5, and then all to the power of 2x. And 8, I can write as 2 to the power of 3, and then all to the power of 2x plus 2. Now I have to do my little distribution here where I multiply 5 by 2x and I distribute 3 into that binomial. I'm doing my power rule here. So that I have 2 to the power of 10x equals 2 to the power of 6x plus 6. Make sure you are distributing that 3 into both terms. Now we can drop the base and set our exponents equal to each other. And now, grade 9, bring the 6x over and we have 10x minus 6x, which is 4x, and then divide both sides by 4. And you get 6 over 4, which you have to reduce. I do not want to see unsimplified fractions. So your final answer here should be 3 over 2. And I also don't want to see decimals. All right, let's go to our next one. So here I have a fraction on the right side, but I know that if I have a negative exponent, then I will turn a whole number into a fraction. So I can write 1/2 as 2 to the power of 1. Or if it had been 1 over 4, I can write it as 2 to the power of negative 2 because I know 2 squared is 4, and then making the exponent negative will give me the reciprocal. So from here, just pause the video and finish this question off, and then come back to check your work. All right, so hopefully you have 8 for y, and be careful here that if you did bring the 7 to the right and you had negative 8, make sure you do divide out that negative 1 because the y should be positive 8. I just chose to bring it to the right, the variable to the right, that way it turns into that positive 1 coefficient. All right, for our next one, I have 4 to the power of x minus 2 and 1 over 8. We should be thinking that 1 over 8 will turn into a negative exponent at some point, but 4 and 8 themselves, they're not super related in that I can't turn 8 into 4 to the power of something. So both of them will need to change base, probably 2. So I want you to pause the video here and try it out on your own. Turn 4 into 2 to the power of something and turn that 1 over 8 into 2 to the power of something, thinking about that negative exponent, and then come back to check your work. All right, so 4 should be written as 2 squared, and then all to the power of x minus 2. And 1 over 8 should be written as 2 to the power of negative 3, because 2 to the power of 3 is 8, and if we make it negative, then we can take the reciprocal. Now let's distribute that 2 in, so hopefully you had 2 to the power of 2x minus 4 equals negative 3, and then back to basics. Okay, so when you set your exponents equal to each other, bring the negative 4 over, it becomes positive, So then negative 3 plus 4 is 1. Divide both sides by 2 and you get a half for x. If you did that perfectly, wonderful. If you made a mistake somewhere, make a note of it so that you don't do it in the future. All right, in our next example, there's one little thing that we have to do before we can go back to the steps that we've been doing. And the problem here is this 7 in front. I cannot have that. I need a term equals a term, nothing around it. So I'm going to divide both sides by 7 first to get rid of that 7 so that I have 6 to the power of 2x plus 3 equals 216. And now back to the same thing. Let's turn 216 into a base of 6 and then set your exponents equal to each other. So why don't you go ahead and pause the video, finish this question off on your own, and then come back to check your answer. All right, so hopefully you got 0 for x. So 216 should be written as 6 to the power of 3. And when we set our exponents equal to each other and we bring that 3 over to the right side, we get 3 minus 3, which is 0. And then when you divide 0 by 2, you still get 0. And that's it for that one. So with this example and the example with the minus 10 right here, you have to do a little modification before you can go to those basics of getting the common base. So if you have something added or subtracted, you have to bring it to the other side. If you have a coefficient in front of your term, one of your terms, like we did here, you have to divide it out first. All right, in the next one, we have two things being multiplied, but both of them have variables. So I can't actually just divide both sides by something, or else I'm just complicating it on the right side. But what I do notice is that 4 and 16 and 64 can all be written as a base of 4. So let's go ahead and do that and then problem solve from there. So 4 to the power of x plus 2. And then instead of 16, I'm going to write 4 squared, all to the power of x minus 1. And instead of 64, I'm going to write 4 to the power of 3. And now, typically, if you see an exponent to an exponent, you would distribute. So I'm going to go ahead and do that. So that we have 4 to the power of 2x minus 2. And now we have to think again about another exponent rule, which is when your two bases are the same and your terms are being multiplied, we can just add our exponents. So on this left side, this x plus 2 and 2x minus 2 can get added so that we can write the left side all as 4 to the power of something. So here's my base of 4. X plus the 2x is 3x, and then 2 plus negative 2 is 0, so that's it. And that's going to equal 4 to the power of 3. Now we can set those two exponents equal to each other. And when we divide both sides by 3, we get 1. So in this scenario, you had to use a few extra exponent rules in that you had your power to power rule over here, but then you had to use your product rule where you add your exponents to get that single term. All right, our last one is probably the trickiest because I see a common base here of 5. I see the subtraction, but I can't just bring this 5x to the right because then I'm complicating the right side for no reason. So what I have to do here is common factor, which isn't something that you might think of automatically, but the problem with the left side in this question is that you have variables in both terms. So if I can factor out 5 to the power of x, that should hopefully fix my problem. So let's try that out. If I put the 5 to the power of x as a common factor, and thinking back to common factors, when you factor something out, you're dividing both terms by the GCF, which is 5 to the x. Now if I do 5 to the power of x plus 2 divided by 5 to the power of x, I'm actually just using my quotient rule, which tells me if the bases are the same, subtract your exponents. So x plus 2 minus x, well, x minus x is 0, so I'm just left with 5 to the power of 2. And then subtract 5 to the x divided by 5 to the x would be x minus x, which is 0, and anything to the power of 0 is 1. Or you can see it as anything divided by itself is 1. Either way works. Now, you should notice once we did that common factor, we fixed the problem because 5 squared minus 1 will turn into a number without a variable. So let's go ahead and do that. 5 squared is 25, and 25 minus 1 is 24. And now, yes, that 24 is kind of useless to me, but I can divide both sides by 24, and then I fixed my problem. So that I have 5 to the power of x equals 25. And now I can get a common base and finish this off. So 5 to the x equals 5 squared, so x equals 2. So like I said, this one's a little trickier, but the clue that you have to do a common factor is that you have two terms that have variables, and they're not attached by multiplication like the previous question, they're attached by addition or subtraction. So that's why we have to factor out the base to the power of x. And that's it for solving exponential equations. So for the most part, if you have a base or a single term equals a single term, get that common base, set your exponents equal to each other. If there's a random number being added or subtracted, just bring it to the other side before you go back to basics. Or if there's a number being multiplied, divide it out. And then the two last special scenarios are these right here, where you have variables in two terms. If they're attached by multiplication, no big deal, just use your product rule. If they're attached by addition or subtraction, you have to think about the common factor.